Hi, welcome to another lecture from Dynamic Economic Analysis. And today we're going to start our final topic where we're going to use all the knowledge that we've accumulated thus far, mainly on differential equations, and it's going to be Solow Growth Model. And we're going to start with assumptions of the model, which we're going to discuss in very much detail. Look, I know that you already discussed this model in macroeconomics classes, but we're going to do extended version of this model, and we're going to do it very thoroughly so we can actually see where all the conclusions from this model comes from. Okay, so first thing we need to do is we need to define production function. And look, our production function is going to be Q equals F of K, A, L. Now, this is a little bit different production function that you are usually used to. But of course, Q denotes level of output, and level of output is defined as a function of capital and AL. What is AL? Well, L, of course, is labor. So we've got that K is capital, L is labor. Now, A, which you probably also know from macroeconomics class, is state of technology. We take here a very economical meaning of technology. So it refers to how well are we combining labor and capital in order to produce goods. Okay, so why do we have this weird construct A times L? Look, because the better is the state of technology, the more productive workers are. Look, you can imagine it as either, if you imagine that L, of course, is the number of workers, K, let's just say, is the computer the worker is using. You can think of A either as human capital, in a sense that how well the worker has been trained in using the computer, or you can think of A as what kind of software is the worker using. So this construct that you see over here, we're going to call effective worker, or effective labor. At this moment, two effective worker we're going to get. So, look, of course, we will get bigger output the more workers we have, but of course now the better is the level of education, the state of skill of each effective labor, for now labor. What is education, or what is the software, or how well are we able to, how well is the worker able to use capital? Of course, it's also going to affect how much we can produce. Okay, so now that we know what effective labor is, let's move on to more famous assumptions that you also probably heard about in your macroeconomics class. So the first one is constant returns to scale. Okay, so what constant returns to scale are? Basically speaking, if we've got some production function, and if I multiply amount of capital by some constant A, let's just say that it's bigger than 1. So we are increasing the amount of capital by 2. We double the capital. Then, if I do the same thing with effective labor, so I double effective labor, of course here the source of increase can come either from increasing the number of workers or improving the state of technology. Then what should happen? Look, constant returns to scale imply that we should get A F of KAL, so A times Q. Okay, what does it mean? Like the best, imagine that, for example, we are doubling capital and effective labor. This means that we will get twice as much production. And this assumption is one of the keys to Solow Growth Model in the version that we're going to discuss. How realistic is this assumption? Look, very often this prediction was tested, and it turns out that that this assumption empirically holds very, very well. Because of course, it might turn out there are some differences. We could imagine that we will have. Still, if this would be empirically obtained coefficient, we are not that far off. So this assumption actually is really well maintained in empirical literature. I'm going to be able to show this to you a little bit better once we're going to use Cobb-Douglas production function. But I think it holds pretty well. Okay, now why this assumption is such a key to us? Look, it actually allows us to transform this model quite a bit. Because look, our production function is of course f of k and AL, right? Capital and effective labor. Okay, look, it means that I can take out of these two expressions any constant I want, right? This is what you see over here. We are taking away any constant we want. So let's just say that I want to take a constant AL. I'm going to have here K over AL and here AL over AL. But AL over AL is simply 1. So look, what I've been able to accomplish right now is to make this function into a function of just one variable. So we don't need this one. It does not affect anything here. So we can write it as AL times C of K. This is a Greek letter. C. I'm sorry, phi, of course, phi. And this is the production function we're going to be working with. Okay, as you see, I've introduced k over here. Lowercase k. What is this lowercase k? Before we go to that, let's just take q that we see over here and the last expression, and let's put them, let's just say here. So we've got q equals to AL times C of k. Now, look, if I divide both sides by AL, I'm going to get an expression like this. So what do we have over here? Maybe let's start with k. Look, lowercase k, the one you see over here, comes simply from that. So k, lowercase k, is this k. divided by AL. So what do we have here? This lowercase k is called capital per effective worker. So it is telling us how much capital we have per one worker, effective worker, of course. Now, how about the other side? What do we have over here? Look, if this is capital per effective worker, then over here we must have output, so level of production per effective worker. Okay, so look, what we've been able to do with assumption of constant returns to scale is to transform the production function we were using to an equivalent form of where we express output per effective worker as some function phi of capital per effective worker. Now, that is very good news for us because we simplified our job quite extensively. But now, how does this function look like? So, with the assumption of constant returns to scale, we are not ready. To answer this question. This is for that reason we need to have a second assumption, and the second assumption is that we've got diminishing returns to factors. Okay, so what does this assumption imply? Look, when we were discussing diminishing returns in microeconomics class, we said that having at least one factor of production constant, we expect that the level of production when we increase another factor of production increases, but increases slower and slower and slower. Look, the best way to see it is, of course, through derivatives. Because, look, if I'm going to calculate partial derivative of Q, so level of production with respect to capital, what am I going to get? This should be positive. Why? Well, the higher is the level of capital, the more we will be able to produce. But then we should also make another assumption which says that second partial derivative of Q with respect to capital is negative. What does this imply? This implies that the level of production is increasing, but is increasing slower and slower and slower. Okay, so knowing this, how could I make a graph where here I have level of capital and here I have Q? Well, assuming that with no capital we cannot produce anything, we will start at this point. But what happens next? Well, definitely, the bigger the capital, the more we can produce. So the function should be increasing. But because the second derivative is lower than 0, it should be increasing slower and slower and slower. So we will have increasing concave shape. Okay, this is not very concave. Well, it's concave enough, but I'm gonna try to do better. So you see the level of production is increasing with capital, but it's increasing at lower and lower and lower phase. Okay, so look, this assumption, diminishing returns to factors, will be the key for us to draw this function, because this is the function we are interested in. So, how do we go about it? Look, we simply need to calculate those two derivatives, but of course for the transformed expression that we see over here. Okay, so how do we go about it? Okay, let's start with the first derivative. So we've got partial derivative of q with respect to capital. Look, this is because this and this is exactly the same expression, so we get that this must be derivative with respect to capital of AL times phi of k. Now, we need to remember that lowercase k is k divided by AL. So in order to calculate this derivative, we will have to use the chain. But look, this is a partial derivative with respect to capital. AL are treated as constant. So first thing we can do is to just take it out in front of the derivative. Okay, and now look. Here we need to use the chain rule in order to find this derivative. How do we do it? Well, first AL stays the same, right? Then we've got derivative. Let's already write it in the form of. We will have derivative of k, lowercase k, I hope you see that this is lowercase k, with respect to, different order, okay. We've got c of k, right? When I need to differentiate this is a function of lowercase k, right? So, the best way for me to differentiate it is to differentiate it by lowercase k, right? But look, here I'm not supposed to differentiate with respect to lowercase k, but with respect to capital K, the capital, not capital per effective worker. So what should I do now? I should differentiate lowercase k with respect to capital. And look, we clearly see that this must be true. Why? Because those two cancel each other out and we get exactly the same expression as we have over here. So, it works. Okay, so now let's get to differentiation. So, AL at front stays. Look, we do not know what is the specific form of this function, so of phi. We just know that this function exists, and that's it. But if it's differentiated with respect to a capital per effective worker, of course, out of this, we're just obtaining the first derivative. So we've got phi prime of k. And now look, the last part is to differentiate lowercase k with respect to uppercase k. So let's do it, let's just say over here. So look, we need to differentiate with respect to k, capital per effective worker. But look, capital per effective worker is equal to capital divided by effective labor. So this, in turn, is the same as calculating derivative out of 1 over AL times k, right? So look, because here we've got capital K, here we've got capital K, this is a constant. So after differentiation, all we've got is 1 over AL. And look, as it turns out, those two expressions are cancelling each other out, And the only thing left we've got at the very end is first derivative of C. Of phi. Oh, what is happening with me today? Now, because we've assumed at the very beginning that this derivative is positive and this derivative is equal to this derivative, we can be sure that the first derivative of this function is positive as well. Okay, so now let's move on to the second derivative, where we will use the tricks we've been using over here. Okay, so what we have now is to calculate second derivative of q with respect to k, right? So we need to differentiate with respect to capital first derivative of q with respect to capital. But we've already calculated this one, right? This one is equal to phi prime of capital per effective worker, right? So, what should we do next? Look, we are ending up at a very similar situation as we had over here. So again, I need to use the chain rule. So, I will get now that this is the derivative of phi prime of k with respect to capital per effective worker times the derivative of k time with respect to capital. But look, we already calculated this derivative. We know that it's equal to 1 over al. And over here, as we do not know the specific form of the function, we can write it simply as phi b's of k times 1 over al. Okay, and look, what else do we know? We know that the second derivative, by assumption, is negative. Now, if we look closer over here, we can clearly see that state of technology and labor cannot be negative. It must be positive. So if this is positive, it means that this derivative must be negative. So we get that the function we were interested in has exactly the same properties as we see over here. So it has positive first derivative and negative second derivative. Okay, and look, knowing just this will allow us to draw a graph of this function. And give me a second to erase this. So look, on horizontal axis, we've got capital per effective worker, and on vertical axis, we've got output per effective worker. Now, again, assuming that with no capital, we cannot produce anything, we're going to start at 0. And then because the function has positive first derivative, negative second derivative, it also must have increasing concave shape. And this is what we wanted to get. We now got this function. So, of course, here we've got phi of lowercase k, and we've got a graph that is showing us what is the relationship between output per effective worker in relation to changes in capital per effective work. Okay, so we've got two main assumptions out of the way, but we haven't said anything about state of technology nor about labor in our model. Look, we're going to take the most pleasant and easy assumptions about both capital and labor growth. Okay, so let's just say that state of technology is given by the following function. A is equal to A0 times E to the power of rho. This is rho times T. Okay. Why am I choosing this form? Because as it turns out, this form will guarantee us that this function will have very nice properties and it's going to be very simple to analyze. Look, what do we actually see over here? We see some constant and then some expression with E. Expression with E means we will have exponential growth. But what is the rate of growth in this case? Well, this is fairly easy to see. First, we can logarithmize both sides and we will get that this is ln A equal to ln A0 plus, we can take it out, right? We will have rho times T times ln E, but of course ln E is equal to 1. So in logarithms, this is how this function is going to look. Now, if I'm going to differentiate this function with respect to time, look, remember, a derivative of ln A will give us what? Will give us derivative of A with respect to time, right? Time derivative. Okay, let's notice now that A with a dot over is given to D is given by DA dt, right? So but of course divided by A. Now this is equal to 0 in differentiation, and here we've got just T, so it's equal to rho. Okay, so what have we obtained over here? Well, this is telling us how technology is growing over time, because look, here we have first derivative of A divided by A, so this is percentage change. This is growth rate of technology, of the state of technology. And let's notice a very pleasant thing about this expression. Look, rho is a constant, right? Because it's a constant, this is the best thing we can get in terms of the simplicity. Because now we see that actually technology here grows at a constant rate. Okay, so now let's try to put this on the graph. Okay, how would we start it? Look, I'm going to try to put 2 here. So first, let's start with this function. Okay? Here here on one axis, I'm going to have A, and on horizontal axis, I'm going to have time. And look, if at time 0, state of technology is given by A0. Now, what is happening later? Well, of course, here we have exponential function. So we see that this function is growing faster and faster and faster and faster. So this is a function A0 times e to the power rho times t. Now, how about if I'm going to put this expression on the graph? Look, what have I done over here? Well, all I did is to logarithmize this function. So, what am I going to get over here? Is going to be ln A. Have we seen something like this? This is a semi-logarithmic scale. Because look, here we still have time, but here we have natural logarithm of the state of technology. And look, if I'm going to put this on a graph, I'm going to start over here and just say at some ln A0, but then it turns out that the growth rate, which is represented here, of course, by the slope of the function, is simply given by rho. So here we've got a linear function, and this, as you see, makes this entire graph very, very easy to use. Okay, so we've got here ln A0 plus rho times t. Okay, so basically all that we said thus far is that another assumption we are taking here is that rho is equal to, by definition, to dA dt divided by A. So, by definition, this is A over A, which means that technology grows at a constant rate rho. Okay, so look, does it mean that technology is improving by the same amount, let's just say every year? No, completely not. Look, it means that it improves faster and faster and faster and faster and faster, but at a constant rate. Remember, that is this base effect we've been talking about before. It simply means that because we are calculating as a base bigger and bigger value, so it requires a bigger and bigger increment of A to maintain the same growth rate. Okay, so clearly here we have a situation when the state of technology is growing faster and faster and faster, but it grows at a constant growth rate. Okay, now for the final assumption, we need to do the same thing for labor. So now that we know the trick, how to do it for technology is going to be very, very easy. So look, now we've got the labor at time t is equal to some L0 times e to the power lambda t. Okay, now if I'm gonna logarithmize it, I'm gonna get that this is ln L equal to ln L0 plus lambda t. Now if I'm going to differentiate it, I'm going to get that growth rate of labor is equal to lambda. And again, I can put my results on a graph. So here I have L, here time, it starts at some L0, and then the function grows exponentially, right? We've got L0 times e to the power lambda t. If I'm going to use semi-logarithmic scale, what is going to happen? Well, again, we expect to have a linear function because we have constant growth rate. Right? So we've got ln L, we start at some ln L0, and the function grows at some constant rate, lambda. So we've got ln L0 plus lambda t. So our final assumption here is that lambda, which is by definition growth dl dt over L, which is by definition L dot over L, is equal to lambda, which means that labor grows at a constant rate lambda. Again, it means that labor, actually the amount of labor increases by a bigger and bigger amount. But because we have bigger and bigger base, to maintain the same growth rate, we require bigger and bigger increments in labor force. Okay, so this is all about assumptions of the Solow Growth Model. In the next video, we're gonna move on to actually putting the entire model together. Okay, thank you for your attention and see you in the next video.